we can talk. Anyone else? You. Amazing, amazing. So let's maybe for 5 minutes, because with Iago and Walter we already checked that it works, and that's probably enough, right? Oh, please, you also have it. Say again. November, December. Yes. Yes, I remember. So if you have 5 minutes, maybe later we can just for the last details. Okay, so, today I think we're going to do something very fun. So, before using this multi-agent system, I mean, you saw yesterday the capabilities of these kind of things. Today we're going to basically see how these agents work, right? And we're going to basically write something very simple. And we will make these agents that basically will talk to each other, and they are supposed to write an idea. And, I think once you see this and you understand this, you can use this really to do maybe other things that are more relevant for cosmology, maybe write code, make plots, maybe write some piece of LaTeX and these kind of things. So I'm going to go a little bit, just a very short presentation. And, I know yesterday we didn't finish with the transformer. So, I still think it's maybe better if we move on to agents. And, if we have some time left, I will come back to transformers. But I think this is really more relevant. So, yeah. Okay, so large language models. So yesterday we talked very briefly about this. So, this is kind of like the standard way that you, let's say you will use ChatGPT, right? So you will have some query, you ask something to ChatGPT, you pass into ChatGPT, and ChatGPT will give you like an answer, right? So that's, like the standard way. But this is kind of, let's say, a little bit limited. You can already do a lot of things with this, but it still is like a little bit limited. So let's talk about agents. So what are agents? So the formal definition is this. So they are, autonomous or semi-autonomous computational entities that are designed to perceive their environment, process information, and take actions toward specific goals, right? So this looks maybe a little bit abstract. So let me give you an example of, maybe a very simple agent to illustrate the capabilities of these things. So let me talk about the REACT. This is basically stands for reason and act. So I always like to put this example. So imagine that your query, you go to ChatGPT, and what you ask is like, what is the result of 4.5 times 3.7, something like that, right? So, the way that this large language model works is like, unless this has seen this answer somewhere, it will probably not give you like the correct answer, right? So in this gigantic amount of tests that it has been trained on, it should have seen, maybe somewhere like what is the result of 4.5 times 3.7 or whatever. So you can imagine that this is like super inefficient way, right, to learn to multiply two numbers. Imagine that, if you have two random numbers, this is not going to be a good way. So what is a good way to basically go around this? So the idea here is basically to provide your large language model with some kind of tools. And in this case, imagine that this might be just like a very simple Python function, right? So you can imagine that this is a Python function where the input is two numbers, and the result of the function is the multiplication of the two numbers, right? Like it cannot be simpler than that. And the way that this works is like, you ask ChatGPT or any large language model, let's say it's like, what is the result of this, operation? And then, like the large language model will say is like, okay, I have access to a tool that is able to multiply two numbers. So what I'm going to do is basically I'm going to call, let's say, this function with the two numbers that you are giving me. This thing is going to give me the result of this function. And then once I have the result, it's going to come back to it, right? So then to the large language model, what is happening is that, it will see the input, it will see the query, what is the result of 4.5 times 3.7, and it's going to see the result of doing this operation with the tool. And then it's going to be basically, given that information, it's going to be able to give you the result. Right? So you can see that this is really like something very simple. And of course, instead of having like, maybe a very simple Python function to multiply two numbers, you can provide this with, maybe a sophisticated code to run hydrodynamical simulations or, something, complicated code to compute power spectra or whatever you want. Is this thing clear? Questions? Okay. So you see that this is like very simple, and this is one of the simplest, let's say, agents that there were. So another one. This is another example. This is RAG that maybe you have heard about this. This is like very popular. So what is the problem here? So imagine that all the large language models, there will always be some kind of data that they will have never seen. So for instance, I don't know, if you write a code, you make a library and you upload to GitHub, let's say yesterday, ChatGPT have not seen the code, right? So it doesn't know anything about this. Unless you train ChatGPT again, it will not really know about your library. But there might be always data that is going to be private, like for instance, medical records, all these things. I think you will never maybe have these to be public available. So but imagine that instead of, I don't know, reading thousands of medical records, if you want to just look for a particular information, how can you use like large language model to do this? So the way that this works is the following. So you start with your query, and imagine that, I don't know, you are a student that are cheating, something like that. And imagine that your task was to read Quixote, this book, and I don't know, you didn't do it, it was too boring or something like that, right? But you have an exam now, and someone is asking you, who married someone, blah, blah, blah. So the way that this works is the following. Is that you take your query. So let's say it's like, who did Don Quixote that? And then what you do is like you embed this into a mathematical representation. If you remember yesterday from the sentence, it's exactly the same thing, right? So we're going to take our sentence, and we're going to create a mathematical representation of that. And now I'm talking about, let's say, the whole sentence. So now what you do is like you take all the documents, for instance, the book. You will take maybe page by page, and then page by page, you will also embed everything there into a numerical representation. So at the end of the day, you create this vector database, and everything that you are doing is basically taking all the book, and you are basically representing it as a, let's say, numerical representation. And now what you do is basically given your query, and given all, let's say, all the pages, you do a similarity search, which is, you can imagine that this is just like what we were saying yesterday, usually is like the scalar product. And the scalar product, if you have two vectors that are very similar, it's going to be large. If you have two vectors that are very different, it's going to be 0 or it's going to be negative. And the idea here is that, things in all these pages that are very relevant to your query will have a larger cosine similarity. And then, for instance, if you imagine that you just take only the embedding of the page with the highest similarity, this will be probably the page with the most relevant information for your query. And then what you do is like, once you have selected, let's say, the page that is the most relevant one to your query, you pass into the large language model your query, and you pass basically like the relevant page. And with this, if you give to the large language model the relevant page and you give your query, it's going to be able to give you like a good answer. So, this is just a way to unrack stands from retrieval, augmentation, and generation. So, just for instance, an example in cosmology, there are these days, for instance, like very, very large collaborations, Euclid, DESI, these collaborations. And some of these collaborations are really so large that I really doubt that there is a single person who, if you ask a question, is going to be able to tell you the answer. But you can imagine, for instance, that you can just embed everything there into a database because, maybe we don't want to do everything public available. And then, you can basically ask questions and you will get, in principle, an answer, right? It's going to be able to find the relevant information, even if you have like thousands of documents that no one has maybe read. Or we're going to see later, for instance, an example of, in my particular case, I ran a lot of numerical simulations. People ask me, has anyone done this? So I haven't really read even all the papers that has been written with the data. You can imagine also doing something like that, right? You can just create one of these things and basically extract the relevant information. Any question until here? Gonzalo. Mm-hmm. Yes. But you mean like the vanilla LLM, like ChatGPT, or what we're going to build? Yes, so for what we're going to do, we will basically have the tools, and we will provide the LLM with these tools. But yes, so for instance, I'm just checking with David Alonso maybe for tomorrow because he has some data from Quaya and it's like, maybe it will be nice tomorrow to maybe try to see if this is able to write a paper. So right now, it knows very well, for instance, how to do NCNC calculation and all these things, and it knows like traditional packages. So for that, in principle, the LLM already knows everything, but if you have maybe some code that is specific or something that it doesn't know, then you will need to use this kind of tools. You will need to extend the capabilities. I don't know if it's clear on that. Yeah, so in principle, no. For this thing, it's like this. The way that this works is that you basically just define the tool, and you just say, okay, this tool is able to do this, and the large language model, in principle, just with that, is able to know how to do this. It's able that if I call this tool is going to give me this result. Without training, exactly. Without training, this is a really amazing thing. I don't even know all the details of how exactly, but yeah, you don't need to train for that. Yeah, please. Yep. Yes. Exactly. So that's a super good question. Yeah, this is getting a little bit updated because, a few months ago or a few years ago, the context windows was maybe 30,000 tokens, 60,000 tokens. So, you can put a lot of things, but it still is limited, right? And small models still have a very limited window. These days, with Gemini, I think it has like 10 million tokens. You can maybe input an entire library there. So, yeah, it's, still, if you have really a lot of things, it will not fit in your context windows. So for those of you that are not familiar, the context windows is, how much text you can feed into the large language model. You cannot fit an infinite text there. There is always like a limitation. And these days, this limitation is very large, but yeah, exactly. That was the motivation initially. Yes. So, it depends on what you want to do. So, for instance, if all your data is text, you don't need a multimodal. But yeah, there are embeddings models that are like multimodal. So you can also, you cannot even like search for text. You can look for figures and, in principle, videos. music, or yeah. Any other question?
What is a token?
Yeah, so a token, you should think about this like one word. It's not really, it's less than one word, but it's, yeah, one word is a good maybe. Yeah. Okay. So let me see. I want to maybe skip this. Just this is maybe more relevant for tomorrow. The agents, are very simple. They are usually designed to just do one task. But, I would say really the magic happens when you really put many agents together. And, as you saw yesterday, for this project, you have agents creating ideas, making research plan, writing code, executing code, writing papers. So, usually there are two different, let's say, modalities on the way that when you have several agents, the way that they work. So, they can collaborate. I'm just putting this thing here is like, if they have to make a meal, maybe one of them is cutting the food, the other is bringing the ingredients, maybe the other one is cooking. So this is a collaboration. But they can also compete, and this is exactly what we are going to use today, where we will have this maker and the hater. And basically, they will be competing. And yeah, so this is important. So again, this is a school for cosmology, so why is Paco talking about this thing? So, the idea of this is that I think this is going to be like super relevant, believe me. I really think that this is going to be transformative. I think the way that we do science in a few years might be very different. So I'm just, trying to give you a tool that might be incredibly useful for you. So, in science, why can we use these agents or large language models in general? So, we can do literature search and summarization. This is very similar to what I was telling you before. You have like a lot of documents, maybe a lot of papers. You can create agents to basically, let's say, read them for you. You can also summarize the papers for you. Another thing is to generate hypotheses, and this is what we are going to do today. So we are going to basically create agents that are, in principle, able to generate ideas. Experiment design, you will see that this is also, in principle, easy. Data analysis and interpretation, they can, as you saw yesterday, they can really analyze data, in principle, from all kind of things. They can also interpret the data. Code generation, again, this is really, I really use these kind of models to code, and I've been coding for probably 15 years, and I think this thing codes much better than I do. So you always have to be careful with these things, but this can help you so much. Cross-domain reasoning and integration. As we were saying yesterday, we might want to take ideas from other fields that maybe we don't know. So for all these kind of things, is like very good. Writing papers, but also critique and refinement. Any question? I think this is all, yeah. Any question regarding this? This is basically just like the philosophy of these agents. You should think about these like, calls to large language models, but they are also able to, do other things. Okay. All right. So let's try to code some simple agents. So I'm gonna go back, and I'm gonna listen to Merdat, and I'm gonna create this in a new tab. All right, so everybody have access to this. And, okay. So, I think there are three main, let's say, I don't know if called languages, but let's say, let's say maybe languages where people, code these agents, right? One of them is LangGraph. That is the one that we're going to be using, but other people use, for instance, AG2. And I think there are other ones like Crew AI. And probably there are many more that I'm missing. So, we're basically just in Google Colab, we're installing LangGraph. This is what we are doing. And now what we need is basically an API key. This is what I was telling you. So this is different to going into the, let's say, ChatGPT website and asking questions, right? Here we are gonna do everything on the laptop. You can do this, let's say, on a Python script. So we need this API key. So the way to get this, let me just wait for this to finish, okay. And for this, you don't really need GPUs. This is already all these models. So the way that this works is that, okay, I'm gonna explain this later, sorry. So, okay, I think I need to update this. Yes. So basically, if you want to use like Gemini, which I think is, more than enough for this, you will need a Gmail account, and then, you can go here. I'm gonna click here. It's gonna bring you to this other page, and then you click here, Google AI Studio. So I'm gonna click here. And it's gonna bring you into this other page. And then I'm just gonna click in Create API Key. And this is free, right? So everybody, I think all of you should be able to get a Gemini API key. And I was talking with Iago and Walter. I think you get $300 for free for 3 months. I think everybody gets this. You should check. It's a very nice. In my case, I already spent it. Second? Yes, you can spend on these things. And these are for free, so it's a very good deal. I don't work for Google or anything, so. Okay, so you got this key. Well, you click in Create Key. And these are things that, again, you should never share with anyone. So I think I'm being recorded, right? So I will need to remove this key later. Where I am. Okay. So, I'm going to execute this thing. And the only thing is going to ask me for my key. And this is the key that I have just generated. So, I'm just copying and pasting it. And that's it. Okay. And now we're going to do something like very simple. Basically, we're going to, let's say, use like the ChatGPT mode, but basically on a Python notebook. So what I'm doing here, let me execute this, is just defining, let me explain this, because this is important. So what I'm doing is basically just defining that, my LLM is basically like the, it's like the Gemini 2.0 Flash. This might not mean a lot to you right now, but there are different LLMs, as we were discussing yesterday. Some of them have more parameters, might be more powerful. Some of them, maybe has been training more recently with more data. So, this is one of the latest ones. Flash is because it's like very fast and it's like very good. It's not like the best one. So, but for our purposes, this is like good enough. So, you are just saying is like, I'm gonna use like the Gemini model. This is the particular model that I wanna use. And I have to define the temperature, what we were discussing yesterday. So remember, the temperature is a parameter that controls, the tokens. The way that large language model works is like, you have some text and it's gonna produce the next token. If the temperature is set to 0, in principle, it's gonna be deterministic. Given a prompt, you will always get the same thing. If the temperature is set to 1, it's gonna be a lot of variation. So it's gonna be more creative. Sometimes too creative, right? So these are things that you need to play with. And then, you are just basically setting like the API key, right? So with this, I'm just saying, I just wanna use this large language model. This is the particular code that I wanna use. I think I execute this already. Okay. And now basically, yeah, please. Yes. What is the criteria? Well, I mean, Google tell you which are the best model. Yeah, I mean, there is another one called Gemini 2.0 Flash, and that's more recent. I think it's more parameters. Yeah, I mean, yeah, no, that's a super good question. So for large language model, people has a lot of benchmark. I mean, if like a lot of things, it's like how well this model works for this or this task or the other task. So that's the way that they really can quantify a little bit the performance of the models. Please. Yep. Seeds? Yes, that's a good question. My understanding of this is that if you set the temperature to 0 and you always have the same prompt, you should always get the same answer. So in this case, there is no seed or anything like that. If the temperature is equal to 1, then yeah, it will make sense to say, okay, what is the seed? But I'm not sure, to be honest. I will need to look into this, yeah. I don't know. More questions? Okay. So now we're going to define basically the message that we want to input into the large language model. So I'm just saying here that this is going to be like a human message. There are 3 different messages for a land graph. There is the human message from us. There is the system message, which is, let me remember, I think the system message is coming from the LLM. I can check this later. And then there is another type of message, which is like I think like the behavior, So, you can ask a question to large language model and say, I'm a cosmologist, because it might be oriented you a little bit more. So, you define your message. In this case, it's like, tell me something about ICTP-SAIFR. And, once you have this is really the way that you, let's say, run the model. So you define your LLM, and the only thing that you need to do is to say invoke and the message. Okay? So this is basically equivalent to just asking something into ChatGPT, but in a notebook. So I'm just going to run it. Okay, so it's executed. So let's see what this thing is. Okay, and this is like what it produces. So you can see that this is an AI message. So now I'm going to say, so human message is our message. AI message is what comes directly from the LLM, and then system message is basically this thing where you can say, okay, you are a cosmologist or you are an astrophysicist, something like that, something that is going to guide a little bit the behavior of the LLM. And there is a content here that is like kind of like the answer, but there are other things. So for instance, there is like, maybe like the model that you use, there is the ID, and then, something that is important is the number of tokens. So in this case, there are 9 tokens, and the number of output tokens that it produces, almost like 500. And then the total number of tokens. So why is it important to know the number of tokens? Memory? That's a good answer. Yeah. Yes. Other ideas? Money, exactly. So for these kind of things, you pay by token, right? I mean, this model I think is free, but basically, yeah, the more tokens that you use, the more that you pay. That's why this subscription that I think many of you have will not work with these things because, yeah, you pay basically by token. So, you can just get, for instance, the content of the result. So this is like the way, ICTP stand for this. Is this a good answer, Rogerio, or not? Okay. It's written on the website, so yeah, exactly. And that's why I probably took it. And the temperature is 0. Okay, so let's try to change the temperature just to see. So let's put temperature equal to 1. I mean, still it should be able to give you like the same answer, I guess. I mean, not exactly the same, but the content should be identical. Okay. But it's not exactly, there might be some words that are different. Okay. So you see, again, you can ask a question maybe directly into your Python notebook, because you might want to get the code directly into your terminal more than asking ChatGPT and getting this thing back. Okay, and this is the way that you get the number of tokens, for instance, like the output tokens, 500, roughly. Okay, so this is just basically the way that you can have your large language model running basically from a notebook. Very, very simple. Any question until now? Maybe. Let's run this again. What's the value per token? Yeah, good question. So, I mean, last time I checked this, I think it was something like, yeah, it varies. It depends, right? So some models are more expensive. I think it's like $1 per million token, something like that. So it's not, I mean, yeah. Any other question? How many tokens per paper? So typically, as I was saying yesterday, it's like $4. So I guess maybe 4 million tokens. Yeah. Okay, so now let's go into the agents, right? So now we have really like the basic setup. That is, from a Python notebook, we are able to call a large language model, and we are able to get basically the answer. So let's discuss about the idea of this. So the idea of this is that we will have some, let's say, description. This could be like maybe, this is the topic that I want you to generate an idea, or maybe, a theme or something like that. So we will have like 2 different agents. So one of them is called maker, and the other one is going to be called hater. And as we discussed yesterday, the idea is that they will be basically talking to each other, and they will be able to come out maybe with an idea. So the first thing that you need to understand is that in LangGraph, we need to basically define what is the computational graph, right? So the idea here is that we need to create what is the way that this thing really works. So in our case, it's like we will start with some description, let's say some topic. This topic is going to be passed into this agent, the maker, who is basically going to take this description and is going to generate an idea given this. And now this maker is going to produce an idea, and the idea is going to be sent to the hater. Okay? And the goal of the hater is basically to criticize the ideas generated by the maker. And then with this criticism, what we're going to do is basically pass this again into the maker. And the maker will maybe go back to the hater for a few times, maybe 3 or 4 times. And once they reach an agreement, which is never, so basically after a few iterations, you will produce your idea. Is that clear? Right, so let me repeat. We start, let's say, with some topic. This agent is going to generate an idea. This is going to criticize the idea. It's going to come back to this. They are going to talk for a few times. And at the end, this agent is going to generate the final idea. Okay, so we have now defined our computational graph. This is like one element that we need for these agents. The second thing that we need for this is an state. So the state is basically, you should think about this like, something that all the agents are able to see. So imagine that maybe, think about this like maybe, some kind of book where, it's going to come to the maker is going to write in that book, and then it's going to pass to the hater, so the book is going to come here, the hater is going to write things there, and then it's going to pass. So it's something that, the agents can see at all times. Is that clear? Yeah, please. Yes. Yep, absolutely. Instead of having like one single agent here, you can have like several of them. And yeah, they can talk to each other and all these things, yeah. Not a problem. Yeah, Walter. So the maker is going to generate an idea, and the hater is going to basically criticize the idea. Oh, because that's his task. That is his task. So we will basically say, okay, this is what you are supposed to do. When you receive the idea, you need to create. It has a very particular prompt. Exactly. Please. The maker knows that. It doesn't have to know that. I mean, the maker will just receive some text, which is coming from a human or the LLM. In principle, doesn't matter. The second iteration, for instance, when it comes back here, this is really coming from the machine. So in principle, it's transparent to that. Yes. So in principle, with the different messages that we saw above, like for instance here, if you have, for instance, something like this, the machine will know that this is an AI-generated message. Whereas if it's a human message, it will know this. So in principle, yeah, you can do this. But I think in practice, it doesn't really matter too much. Other questions? Okay. So for the state, for instance, will be something like, what is the idea? Maybe we have some, and think of this like a Python dictionary, where we will have a field that is called idea. And every time that we generate a new idea, we will keep this field there. Another thing can be like criticism. This is, not sure. Another one can be maybe like the iterations, how many times they have been talking back and forth. And the idea is that this thing, every time I send to this agent or to these agents, they will be able to see this state. They have access to this. And this is kind of a memory of everything that happened before. Yeah. In principle, yes. We're not going to do anything multimodal today, but yes. And I think it's going to be easier if I maybe just show you the code. Any other question? Okay. So let's go here. So, this is the way that we are going to define our state, like the state of the graph. So this is basically like a Python dictionary where we have, let's say, I'm not sure how this is called, maybe like an entry. So one of them is like the topic. What is going to be the topic of the idea? We will have another field that is like the previous ideas. So, we not only want to generate ideas, but we want to keep track of all the ideas that has been already generated. Another one is going to be just like the idea itself that we want to keep. And this is like the previous critiques. So we want to also keep track of all the previous critique that we have done. And then just like the number of iterations. Okay, so this is like nothing, just basically a Python dictionary. And now let's create our first agent. So this is going to be an agent already. So, the first thing that we need to do is to say, what is this agent supposed to do? And, this is basically like we need to define what is the prompt that we're going to use. So, the idea maker, the prompt is going to be is like, given the topic below, generate an interesting idea for a science project. Take into account any critique provided and previous generated ideas, if any. Ricardo, yes.
Can I input some criticism? Because I already know that I want to answer to some specific questions.
You mean?
I input some criticism. I can play the role of the hater, at least partially.
Oh, you mean that you want to be the hater?
At least partially, the only one.
Yes, absolutely. You can input human feedback at any time. Yep. Okay, so basically given this, and the only thing that we're doing here is say, okay, so the topic is basically the topic, and this is coming from the state, from your graph state, and we are basically just copying and pasting the previous ideas generated, and we're also copying here like the previous critique. So when you generate an idea, you take into account all the previous ideas that you have generated here, and you also take into account all the previous critiques. Is that clear? Yes.
The first iteration, the previous idea, like the first time we are calling the previous ideas and previous critiques needs to be filled in?
Very good question. So exactly. So if this is like the very first time that you call this agent, previous ideas is going to be empty, and previous critique is going to be empty, right? Because we don't have anything. That's a very good question. Okay, so that's it. This is really the prompt for my agent. And now what I'm going to say is like, this is my LLM that I have defined in the same way as before. I'm going to basically invoke the LLM with my prompt. And I'm just going to increase the number of iterations by 1. And I'm just basically extracting like the content of the result. I don't care about the number of tokens and all these things. And then what I'm saying here is that, now I need to update these previous ideas. So the thing that I generated, I need to basically, the new idea that I have generated should go into the previous ideas because it has been already generated. Is this clear? This is really like, a super Super simple agent. So let's execute it, okay? And then, we now need to define this idea header. So it's really the same thing. We need to define a critique. So we need to define a prompt. So the prompt here is like critique the proposed idea in order to improve it. Take into account all previous ideas and critiques, if any. So what we're passing is basically the topic. We're saying, this is like the current idea that the maker has made. And these are like the previous ideas that they were generated, if any. And if they were also critiques, we're gonna put it here. And then, we define our large language model. We basically invoke with the prompt. And that's it. And basically, we update like the previous critique. Interesting. I didn't even look at this, yeah. Yeah, it was probably by chance, yeah. No. Yeah, let's do it, yeah. Not sure if this will be, yeah, but yeah. Okay, so, that's really our idea header. You mean here? Yes, so what we're doing here with this thing is basically, let me write it here. So you should think of this like, so it's gonna be like previous ideas, and this is gonna be like, let me see. So it's gonna basically put, all the things that it has generated before, and now it's gonna have a line that is gonna say iteration 1. And if you now do to the iteration 2, you will keep this, but you will have more ideas here, and you will have iteration 2. Because the LLM will, is able to see that, it was generating this, it was improving on this, so it's good to keep this kind of thing. Yes. That's a good question. I think the way that we have put it here is going to look at everything that was there, but it should be able to, but yeah, I think it's going to take into account everything that happened before. No, I think what is going to happen is that it's going to criticize the latest idea, but taking into account all the previous feedback. Like for instance, if before it gives a feedback about improve this, and it has already improved it, it will not tell you again to do this, because it has already done it. The Yes. So in principle, the more iterations that you have, in principle, it should be able to improve the idea more and more. But as we were discussing the other day, these things don't really converge. As I have never seen, say like, okay, no, this is already amazing. Let's keep it like this. I have never seen that. Okay, so, the other thing that is important is that you don't need to have, the LLM for the maker doesn't need to be the same one as the LLM for the hater. Actually here we can put maybe 2.5. This could be like 2 different LLMs. And actually, this is like very good because the same LLM might at some point reach an agreement with itself. Okay, so I'm gonna execute this. And now, basically, this thing, the only thing that I'm doing here is basically saying that, let me see. If state, yeah. So basically, this is the way that we, when we define the computational graph, there are some things that there is really no, there are things that it will always be like this. So for instance, I will always go from the description into the maker. From the description, I cannot go to the hater. From the description, I cannot go directly to the idea. From here, I always go here. But from the maker, I can go into the hater, or I can go into the idea, right? So when do I go to one, and when do I go to the other? So that's exactly what this function is doing. So what this function is saying is that, if the number of iterations is less than 3, the maker should always go into the hater. But if the number of iterations is more than 3, then the maker should go into the idea. Yeah, so just basically, the way that you define your computational graph. So I'm going to execute this. And this is like, now what we're going to do here is basically building the graph. So, this is the way that we define this. This is, you define your state and you define your graph. And now what you say is like, you define your agents that you have. So in this case, we have only 2 agents, the maker and the hater. So this is the way that you define this. You add node, and then you add another node for the hater. And then basically you need to define how the edges are connected with the nodes. So what this is saying is that from the start, from the very beginning, you go into the maker. From the hater, you always go to the maker. But from the maker, you use this function that we defined before in order to see if you go to the hater or you go into the final idea. Okay? And then, yeah, this is like basically nothing. This is just building the graph. So I'm going to execute this. And this is the graph, the computational graph that we have. You start from the beginning, you go into the maker go into the hater, or can go to the end. That's why, you have these 2 possibilities, but the hater will always go into the maker. So it's exactly the same graph that I put here. Okay, so let's run it. That's it. Yeah, please. Yeah. So let's think about this. Yeah, for instance, you can have maybe 2 agents, each of them producing an idea, and then sending both ideas into the hater, something like that. A single agent can also produce 2 ideas. Could be different LLMs, different. What do you mean? Yes. Okay, so this is what I was saying. So right now, for our maker, the model is this 2.0 flash, but for our hater, the model is 2.5 flash. And actually here, you can put like OpenAI or other model, and it's fine. Yes, in our code, we use like different agents. That's why we need like OpenAI and Gemini. Yeah. Okay, so let's run it. So now we just need to define our input, right? So let's say the input is large scale structure. Maybe we should do something more specific. Anyone has any topic that we would like to generate an idea? Okay, scaling relations of galaxy clusters. Okay, so we define the topic. Previous ideas, there is no previous idea, so we leave it empty. We don't have any idea right now, so we leave it empty. Previous critique, we don't have anything, so empty. And number of iterations, 0. So this is your input state. And now the only thing that you need to do is to basically run the graph. So let's do it. You can complement if you already have an idea. You can say, okay, so for instance, it's like, okay, let's brainstorm an interesting, something is, okay, first let's clarify what we're dealing with. Okay, yeah, it's super verbose. The idea is galaxy cluster growth, emerging, blah, blah, blah. Okay, we will need to read this carefully, but now let's look at the critique, right? So it has generated the idea, now it's sending back into the critique. It's highly relevant. Okay, so it's saying this is like the good things, and then areas for improvement. Okay, so it's basically saying, you need to be more quantitative. Scatter. I guess maybe from the scaling relation. No, I guess probably, the scaling relation you will have some scatter, so. Okay, yeah. But it's giving you here some criticism, and then, it's coming back to the maker, and it's like, oh, the critique is excellent. This reminds me when you reply to a referee, right? It's like, we thanks the referee for his or her constructive. Okay, so I think this is the core idea. Determine how the scatter of key galaxy cluster scaling relations, I guess these are luminosity versus mass, I guess temperature, maybe this is, I'm not sure. And then the YSC, okay? Okay. So, it's coming back into the critique, who is gonna give you, it's kind of really, all these things are really, it's good, I will say. Please. What do you mean? Not sure. Uh-huh. I see. Yes, so in this particular case, no. Basically, I think, let me rephrase what you're saying is that there is already some context, right? When you call the LLM. So in this case, no, the context is 0. When you start from the beginning, there is nothing there. So it's completely empty. But then it accumulates, right? When you generate the idea, when you criticize the idea and these things. Yeah. Please. Yes, it's going to stop exactly. Well, the model will know because when you're running the computational graph and you come to this agent, it's gonna see, okay, so where do I go next? Because that you need to define your computational graph. So the way that you go next is like if you have less than 3 iterations, you come here. Otherwise, you come here. Exactly. That's the way that we have built the graph. So the graph basically, you need to define your nodes. There are 2 nodes, these 2 agents, and we need to define the edges. So the idea is that when we come to this agent, we need to define where it's going to go next. It knows because all the agents have access to the state. And here, there is this iteration, so we are updating constantly this thing. So it knows this. Yeah, Belén. Absolutely, absolutely. I mean, for the things that I showed yesterday, I mean, we have a gigantic graph, right? There is a lot of agents there talking and yeah. More questions? Please. You can do it. I think the idea of this will be like, yeah, you ask the question and then you have to ask again, okay, now criticize, now do this again. So exactly, I mean, this is kind of a way to do this in an automatic way. Otherwise, you will need a human for every step. Yeah. Please. We could have human feedback. Right now, it's not implemented to have human feedback, but you could have it. Yes. So, for instance, I mean, something that we could do is like here in the idea hater, beyond this, we could say, okay, now give me some human feedback, right? And then you can say, okay, forget about galaxy clusters. Look for scaling relations in dwarf galaxies or whatever. So in principle, it's going to take this feedback and it should be able, I think, to change completely the idea, I think. Please. Mm. Yes, yes. So I did this in the past, and as I was saying, they will never agree. The hater never agrees. He will always find something. That's a good idea. That's a good idea. It's like, maybe if the hater already doesn't, I mean, the criticism is not really relevant, maybe kill it. So that's a very good idea. You can have another third agent checking this thing, and I say, look, stop here. I haven't done it, but this is a good idea. Maybe it's a good exercise. I think you have a... I see. Yeah. Okay. So let's see. So, I mean, I think this is probably the last thing that it generated. So let's take a look at the very end. So the final idea that it generated, let's see. Disentangling the impact of agent feedback and mergers on the core properties of galaxy cluster and their scaling relations. Okay, these look like very fancy. Let's see. So I guess it's looking at these properties. And it also gives you like the potential challenges.
You didn't start with any data. You let him ask.
Yeah. I mean, everything that we ask here, I mean, the only thing that we have input is the topic, which was the one that you suggested. That was really the only thing. Okay, so that's it. So again, maybe you don't want to use these things to generate an idea, but now imagine that it's very simple, for instance, to say, okay, I want to write a code for doing this particular calculation. So you can have an agent writing the code for you. You can have another agent maybe executing the code. And, usually maybe there will be a bug, right? So what you can do, and this is the way that we do things, is like, you can take, I mean, if the code has a bug, it's going to give you an error. right? So you can have an agent where you're going to have the code, you're going to have the error, and you can ask him, fix this. And in principle, should be able to write the code and improve it. And basically, these are the ideas that we have in this multi-agent system where you can, in principle, do things in an automated way. So again, even if this looks like very abstract, believe me that this is, I think, is the future, I think. I might be wrong. But it's a very, very powerful, incredibly powerful tool. Questions, comments, complaints? Please. Oh, you mean whether you can see, for instance, the code that it writes, how... Yeah, in principle, as you have seen, it gives you everything. So you can have the code, also the error that it code. You can keep track of all these things. Please. If you design the system to be like that, yeah. You can have, I don't know, some idea. You can say, okay, write a code to do this. And then, you can have an agent writing the code. You can have another agent maybe executing it. And yeah, everything could be automatized in principle. Yeah. Yeah, that's a good question. I mean, whether you define an agent to do a super small thing or something larger, yeah, I think, for instance, this thing you can say, okay, there are two agents here, or you can say, this is just an agent, right? This is an idea generation agent. Yeah, I think maybe this is just language. What I do, oh, you mean like if I have really a paper and I want to summarize or read everything, I will probably just have an agent going section by section, something like that, or page by page. Yeah, but it's going to be only one. I don't need to create several for this. Please. Yeah. No, that's a good idea. Yeah. So, yeah, the number of tokens is kind of, I mean, it's set by other reasons. You cannot have a gigantic vocabulary and these things. Yeah, no, I think a good way to think about a token is really like a word. And yeah, I don't think you have too much flexibility on how many you get and these things. No, I mean, at the end of the day, believe me, it's not really so much about, I mean, of course, the number of tokens is important. You will pay more. But at the end of the day, what you want is a very good model that even if, I mean, I will be very happy even if I use double of tokens, you don't make bugs, for instance, in your code. If you have something that uses very few tokens, but it has a lot of bugs, and I have to keep improving, at the end, it's like, yeah. So I don't think it's a super big. Mm-hmm. Yeah. Okay. So maybe we should discuss, for tomorrow. So, I know that this is maybe getting a little bit out of the out of the weeds. So will you guys be interested tomorrow in doing this exercise? Maybe we all together, we sit down, we use the codes, so you can see how to, maybe you can write papers, or, I can talk about, other things, maybe, machine learning methods. I can go deeper into transformers, or, maybe graph neural networks. Someone was asking me, let me know. Who will prefer, for instance, to write papers and use this code? Okay, not so many. That's good, that's good. Who will prefer maybe more, let's say, traditional lecture about, I don't know, graph neural networks or a particular model? Okay, good. Okay, still fewer, I will say. Any other idea that you would like to? I mean, this is, of course, for you, right? We need a hater. Okay. Exactly. Exactly. That was my plan. So I will do this there, and I will explain in detail. You need to install like this, like that. But still, might be interesting if a few people maybe can also do this. So you can really do, and you see. So let's try to do both. Like. Well, you saw yesterday 25 minutes, but then it might take longer. So you mean like a lecture and writing a paper at the same time? multi. Okay. So when you really want to run, no, you need to go down more. So it's basically like the very last part, like this one. This is where you define the topic that you want. Oh, sorry. Yes, please. That's a very good question. So the way that you will do with this will be to say, okay, write some code, and it's going to do it. And then all the text that it's going to produce, because you can take it, you can take this text and put it into a Python file. It's like, hello.py. So you put it there. And then, you can also execute code, even in a Python notebook. There are ways to, commands to do this. And then if there are an error, you can also retrieve the error from that. And then the error, you can pass it, if there is a bug, you can pass into another agent. Say again? Yes. So, for instance, in practice, for instance, the way that we define here the content, so this is like text, right? So why is it not working now? So give me 1 second. So let's do like this. Okay, so this and this. Okay. So for instance, here you have already some text, right? Which is this thing here. So what you can do is to say, like, I don't know, how do you save tests? NumPy save tst my file.py, and then you put here result.content. And I probably need to import NumPy. Okay? So this maybe will work. Import NumPy as MP. Classic, yes. NumPy save tst is expecting a 1D array. Okay, I don't remember exactly right now, but it's basically this philosophy. And then, you can have this in a file, and then another thing can run and execute that particular file.
There's also, okay. Is there also maker and hater interactions within the code? Like a hater that says, no, this code's not so good, perhaps you should do that and go back, or no?
So we have a few agents that is going to check in what the other agents are doing. But in particular, it's coming from bugs, right? So if you have a code that it doesn't run, it fails, then it's going to come back. So it's not really like a hater, but it's kind of improving the code itself.
Okay, so the hater and maker is just for the idea?
It's only for the ideas, yeah.
Okay.
Yeah.
Thank you.
Yeah. Well, yes. So in principle, we just need to define really like the text. So let me see. For instance, this is the thing that David has sent me. I'm going to check with him if we're going to use this. But for instance, he has some data here for Quaya, which is a quasar catalog. And basically, he has compute like the cross correlation with CMB lensing. So basically, he has a file to use this. And this is like, for instance, the way that you read the data. And then we're just asking to say if it can do like a cosmological analysis. Yes, so right now for the input, we cannot use multimodal capabilities, so it has to be text, unfortunately. But if you have any data, it can analyze the data itself. It's just that in the prompt itself, we cannot put images. Okay. Yeah, please.
For example, we have some pipeline that we could follow, thank you. Like, for example, some part of the code are supposed to follow already prepared and code. Could we just inject that to the input and say, or not like a text file, but also, I don't know, a .py or a notebook to follow in order to...
Absolutely.
Okay.
You can copy and paste. This is a little bit what we did here with a bit. So this is kind of like a Python notebook, like a simplified one, and we just copy and paste there.
Yeah, of course, I'm talking about more difficult, like more elaborated pipelines. So.
But in principle, yeah, there is no problem. I mean, if it's like hundreds of thousands of lines, not sure if it's going to work well. But yeah, no problem. You can just use something thousands of lines. Should be fine.
Thank you.
We are seeing all these agents like all are general purposed, right? So it's a general question, but are there any are other agents like more specified like for some purposes, or it's, I don't know, this is the question.
You mean like large language model that has been fine-tuned for some?
Yes.
Yes. So yeah, these are of course generic large language models. I know people has fine-tuned this even for astronomy, but yeah, we are not really using those ones. But you can do it if you have a particular goal. Or
do you think there's a improvement with the?
So what I know, I mean, other people might have done this. That, for instance, some LLMs has been fine-tuned in literature search. So maybe papers from the archive. Because if you go to ChatGPT and you ask a question about something, sometimes it might not give you like a good answer. But some of this model that has been fine-tuned really with papers from the archive in AstroPH, for instance, it's going to give you like a much better answer because it has been really fine-tuned for these things. So these kind of things, yeah, not sure if that's well. You mean to use this code or?
So in this way, AI will read those papers and write the paper or the code based on those papers that I sent, that I passed?
And to train.
No, like a reference. Like I want you to cite this paper, and this paper has a method that does this. Based on this, do that.
Yeah, so the way that I will do with this, again, maybe with other things, is like I will copy maybe the methods in that paper, put it here, add the archive numbers that you want to be cited, and in principle, that should be maybe enough, I think. As always, you need to try and see.
So ChatGPT usually has this thing that it remembers sometimes the thing that you asked before. Does this or the other the scenario thing erases memory every time that you run it in order to have like not be biased about previously things?
Yes, that's a very good question. Yeah, so this by construction, initially there is no context at all. And then you really, with this state, you are keeping track of the context. And yeah, you can be sure that you erase the context because otherwise you end up paying a lot of money, right? Everything that you have in context is tokens that you use.
I see.
So in this case, you really control, you have full control. When you use ChatGPT, I think you don't really have control of that. With this, you fully control what you have. Yeah.
We should have tokens for questions.
So, more technical question. Will we need GPU to write the papers for tomorrow? Can we do this locally?
No, you don't need GPUs.
Okay, so the monster of GPUs are only the convolutional neural networks. Agents do not need them.
Yeah, I mean, if it decides to do some deep learning techniques, yeah, it might not finish in 1 hour and a half. Yeah, let's see. I mean, yeah, sometimes, yeah. I mean, these papers that I'm writing for David is supposed to be taking only like 20 minutes, and it has been since 1 a.m. So, yeah, so it's sometimes, yeah. This CNC is super slow. I don't know what is, but yeah. Yeah, Yeah, we're testing if, to see if this is going to work or not. Yeah, so it's doing the NCNC. Yeah. Yeah, so we need to ask David for the details, but David has sent me this data. So these are, is basically, if I understand correctly, is the cross correlation between the qualia and the CMB lensing, and basically we're asking to extract the cosmological parameters from it. No, this is the prompt. You can see here the prompt, and I think we wrote here, the goal of the paper is to obtain the cosmological constraint on sigma 8 and omega matter from these constraints.
Paco, and have you published a paper made it by this or not?
No. Many people. I mean, you will see tomorrow, right? I mean, the papers are still easy to know that they are AI made. You will see that, for instance, the citations are a bit weird. That doesn't mean that, if you take any of these papers, you work for 1 day, I think will be, and if it's a good paper, it's going to be incredibly hard to know if this is a true or AI-generated paper. Some people are asking me to to do these things. It's like send to a journal and see if it gets accepted. I think if we do this, the editors and the journals will get very angry. So this experiment was done in machine learning precisely this year. So again, these are ideas coming from machine learning. So this year there was one of these big conferences, and one of the papers was accepted. And in principle, these are papers that are reviewed by 3 or 5 referees, human referees. You don't know. So that was it was a kind of breakthrough, right? I mean, you have a full AI-generated paper being accepted in a top machine learning conference. So in this case, what they did was to do this thing with all the editors. They told the editors, and everybody was aware of these things. They submit 3 papers, only one was published. So, I mean, Rogerio sent me today also an article about all the predators, journals. Yeah, I'm pretty sure someone will use this thing to send one of these very bad papers. But if you can write agents to make papers, I think it's going to be easy to also write an agent to detect if the paper is AI generated or if it's a bad paper, right? So this paper, if you do something like that, I mean, at the end, it's going to be up to you, right? I mean, at the end of the day, this will reflect and it's going to be your responsibility. Sorry.
I mean, very polemic comment, but the writing part is not the hardest one, so you can just make a paper and you write everything, and no AI will detect that the analysis was made by an AI and the idea also made from an AI agent. Just a comment.
You mean use this to do the idea, generate the plots, but you write it? Yeah, exactly.
So maybe for tomorrow you can make a quick agent to try to judge if these 3 papers are real or not, and then you feed some other real papers and see if it gets corrected or not. That's a quick exercise.
Yeah.
But maybe a short training is not enough. But
yeah.
You think it would work or not?
I think so, at least with the papers that is generating. I mean, depending if you put citations or not. Yeah.
My question it's about your homework or your work tomorrow. If I put in the prompt and for say, I would like to do one no parametric method with this data, the AI it's possible to create like I don't know, run the Gaussian process or another no parametric approach for analyze the data.
Yeah.
Oh, okay.
Yeah. If you have some data, yeah, let it know to your representative, and we can use it. Someone already sent me data, right? So William, yeah, you already sent me the data, right? And I think someone else, right? I think I got another email with some data. So tomorrow we can try and see what produces. Okay.
Okay. Thank you.
Thank you.